Hello, welcome to N23 Covalent Bonding, focusing on hybridization. There is a lot going on here, so I do strongly suggest, if you're watching this by yourself, to kind of read through, listen, pause, and kind of go through it, but there's, again, a lot of stuff. So, hybridization. At the end of the day, it's just the blending of orbitals. So one way of looking at it, a poodle and a cocker spaniel. Another way of looking at it is a bulldog and a shih tzu. Let you take that one for what it's worth. For our purposes, we are blending s and p orbitals to make a hybrid orbital that looks kind of similar to the p, way different from the s, but again, it's a blend of the two put together. So we want to figure out initially what proof exists for hybridization. And to do that, we are going to take into account the molecule of methane. So here's our methane molecule, and it's simple: 1 carbon, 4 hydrogens, 4 bonds, very easy. It's a natural gas, and it's a very simple molecule to see what's going on. Now, interestingly, initially, in our examinations of methane, we have found that all 4 of these bonds between carbon and hydrogen are identical in both bond length and bond energy. And that's going to play an important part as we go through this. So if we look at carbon's ground state configuration, we get this. And hopefully we all agree this is what we should get based on its electron configuration and here as an orbital diagram. But hopefully we can see a problem on what's going on. Because originally we saw methane with 4 bonds. But the problem here is, according to this diagram, carbon can only make 2 bonds. So you look at the unpaired electrons. Unpaired electrons have the ability to receive another electron to make a bond. Paired electrons do not. So just based on carbon alone, it only makes 2 bonds, yet we know methane exists with 4 bonds. That's kind of a problem. So as we said, concluding that carbon only has 2 electrons available for bonding, but that is not enough. So those 2 are available, but carbon does make 4 bonds. So carbon somehow overcame this problem to make 4 bonds. What are some possible ideas that carbon could come up with in order to go from making 2 bonds to making 4 bonds? That's a thought we need to have. Well, again, the first thought, chemistry or chemists, was, well, what happens if carbon promotes one of the 2s electrons? So the blinking one here in red, we're going to move it to the empty 2p orbital in order to, see what happens if it helps us overcome our issue. So if we do that, then carbon does this. Well, looking at this now, carbon now has 4 electrons available for bonding, and it should give us 4 bonds. Our problem is solved. We are good to go. Right? Question mark? But quickly they recognize there's a problem with this arrangement that we just saw. Again, here at the bottom, they found a problem with this arrangement in the bottom diagram. 3 of these carbon-hydrogen bonds would involve an electron pair where the carbon electron is 2p, and that matched with the 1s electron from hydrogen. So these ones blinking in the purple, they all match. And that helps. That's helpful. 3 bonds. But again, methane has 4 equal bonds. Well, this would mean that 3 of the bonds in methane would be identical in bond length as well as bond energy, because they would involve electron pairs of equal energy, some from 2p and some from the 1s of hydrogen. So those 3 bonds, they're identical. But again, we know carbon has 4 equal identical bonds. So what about this fourth bond? Why is it different? What's going on with it? Well, if we look back to the orbital diagram, the fourth bond is between the 2s electron of carbon and the 1s of hydrogen. 2s from carbon is not the same location or energy as a 2p from carbon. So this bond would be slightly less energy and different in its length due to the fact of where these electrons are located. So the bond would have slightly different characteristics than the other bonds. Again, any difference suggests it is different. But again, all 4 bonds in methane are identical. So that's the bond we're referring to right now as the problem child. And this difference between this bond blinking and the other 3 bonds is measurable to a chemist when it comes to bond length and bond energy. If it's measurable, then you have to kind of accept it for what it is. But when they did research on methane, did they observe one bond was different than the rest of the bonds in methane? The simple answer is no. We've been saying the whole time here that methane has 4 identical bonds. These ones. So again, measurements show that these 4 bonds are identical, they are equal. So we have to come up with some other explanation to explain, that's redundant, but hey, why not, what's going on with methane? So this is where they proposed hybridization. Mother Nature figured it out long time ago, but now here we are. So to define it, hybridization is the combining of 2 or more orbitals of nearly equal energy within the same atom into orbitals of equal energy. That is what hybridization is doing. So in the case of methane, we call this hybridization sp3, meaning that an s orbital is combined with the 3 p orbitals in carbon to create 4 equal hybrid orbitals. As you can see, the 2s and the 2p kind of come together in between to make 4 equal energy orbitals. These new orbitals, again, slightly more energy than the 2s and slightly less energy than the 2p. So somewhere in between, not an exact dead center. The 2 in here just means it's 2s and 2p. That's irrelevant. All we really care about is the fact that it's a single s orbital and 3 p orbitals, giving us the name of sp3. So, another way to look at sp3 hybrid orbitals. From an energy diagram, we can see, again, that we have our single s and our 3 p orbitals, and then they hybridize together to make 4 equal energy sp3 hybrid orbitals. Notice it's 1s and 3 p's. 1 plus 3 equals 4. That's where the 4 orbitals come from, because you're using 4 individual orbitals to make 4 hybrid orbitals. Let's back up to sp hybrid. We know that sp3 hybridization in methane, there are other types of hybridization in atoms that does occur in different molecules. So these include sp hybridization for this example, in which we use one s and we only use a single p orbital of the 3. So from our diagram we've seen before with sp3, we are only using a single s and a single p. 1 plus 1 equals 2. Notice on the right-hand side, we have 2 hybrid orbitals and 2 unhybridized p orbitals. So sp is just made from one s and one p. That's all we're referring to. sp2 hybrid, other one left. Again, made from an s orbital and two of the p orbitals or sublevels. Again, same diagram. Notice that we have 1 plus 2 is 3 hybrid orbitals, and that leaves us 1p that is unhybridized. Questions on hybrid orbitals? Okay. So back to this chart, which we've seen before. The hybridization we are referring to is only the central atom, the A in our AX formula. Now, notice something here. AX2 has two things bonded to the central atom. Go to the hybridization, it's sp. sp hybrid is two orbitals or two hybrid orbitals. Go down one. AX3 is three things bonded to the central atom. Hybridization is sp2. 1s plus 2p equals 3. Hopefully the theme you're picking up on, the hybridization matches the steric number. AX4, four things around the central atom, is sp3 hybrid. There are four sp3 hybrid orbitals to bond with four things in AX4, or have a lone electron pair. These hybrid orbitals have the ability to move around and go anywhere within the molecule. That's why when we start adding lone pairs, we get different bond angles than when there is no lone pairs on the molecule. All the p orbitals before hybridization are stuck at the x, the y, and the z axis, 90 degrees to each other. Mathematically, the wave function that explains orbitals, that's where they're at. These hybrid orbitals are not stuck anywhere. They can move and perform any angle necessary to make the shape work out due to the valence shell electron pair repulsion. That's the great thing about hybridization. Now, the bottom two rows, there are question marks. Years ago, Ds, or empty d orbitals in atoms, had the ability to make hybrid orbitals using s, p, and d orbitals. That has been disproven, and we're kind of in a holding pattern, waiting to find out if that was a mistake or if there's some other method or mechanism which supports an expanded octet and its hybridization. We don't know that yet. Any questions on hybridization and molecular geometry? Okay, thank you.